Something every programmer needs to know is the cost that the computer faces when dealing with memory. You are always going to be dealing with data in some way, shape, or form if you're programming anything, so you need to know how it is kept. From your registers, to cache, to RAM, to storage, all of it is arranged exactly the way it is for optimal performance. And the best way to look at this is in the form of a hierarchy. As we go from the top of the hierarchy to further down, we can see that memory goes from more expensive and a lot faster to a lot cheaper and a lot slower. We're going to be focusing on these, as I only put LAN calls here, just to make a point about them in the end. Now, before we actually get started, I want to make one very important clarification. See, when I use the word expensive, what I mean is that this piece of memory takes up more power and takes up more critical space on the CPU. Now, let's start with the very top of this hierarchy, the register, which is the fastest piece of memory on a computer. It is small enough for hundreds of them to fit on your CPU. They are crucial to program execution and state tracking, and every piece of data you work with gets operated on in these registers. Here's how that works. Data gets requested from memory, and it is written to a register in your CPU. In that CPU, the value gets read from the register and operated on in the arithmetic logic unit. Then a new value is written back to that same register, and that data from that register is written back into memory. Here are the different types of registers. We got data registers, which mostly hold integer values. There are address registers, which you should really only use to hold memory addresses. Floating point, which is used to hold floating point numbers and for floating point operations to happen. General purpose registers, which you could really use for anything. There are status registers that decide conditional branching. We have a program counter, again going back to execution and state tracking. Temporary data buffers and instruction registers, which holds the current instruction. This is the most expensive form of memory because these are made out of flip-flops, and that circuitry draws a lot of power and is not very compact. But this is how it maintains access in one cycle. Let's go to the next level down. Cache. This is the closest and fastest non-register memory, which is also very, very expensive. It is here to reduce time to load data from the main memory. Here's an example of a processor right here. We can see here that there's a L2 cache. This is not the smallest it gets. Let's start with L1 cache, which is the smallest. This sits right on one CPU core and is used only by that core. It holds about 64 kilobytes. And the address line from your memory that has your data on it comes here first. Then there's L2 cache, which is usually shared between two CPU cores, holds about 256 to 512 kilobytes. The least used cache from L1 gets bumped down to here. Let's go back to our example again. This is a dual core processor. We can see here that there's one core, there's another core, and one big L2 cache. Since there's only two cores on here, it only really needs L2 cache. Now let's go down to L3. This is shared between all the cores of your CPU. It is also the slowest form of cache. This stores up to 8 megabytes, and the least used cache from L2 comes down here. This is all static RAM. To store 1 bit, it uses 6 transistors. And then we have dynamic RAM, which to store 1 bit, you need 1 capacitor and 1 transistor. These are what are used in your RAM sticks. This is your dynamic RAM. Everything that the program uses, even the program itself, is stored here. Now, in a DRAM cell, the capacitor holds a temporary charge, but it needs to keep getting refreshed, otherwise your data is going to be lost. This makes it slower, but that's also how we get it to be so compact. This, along with a lot of other factors, is how we keep it decoupled from the CPU so it can be swapped out. Next level down, non-volatile storage. Your file system, your data, your operating system, your programs, everything that is not in use is stored here. It does not need power to maintain data, and there are many ways to go about it. We got magnetic storage with our hard disk drives, and we also have flash storage. And there are also many ways we can store more data in a more compact fashion. Just take a look at this USB drive. This small thing is about the size of a finger segment. This holds 256 gigabytes. Now let's look at the access times for each of these forms of memory. Registers take about 1 cycle, L1 is about 4 cycles, L2 is 10, L3 cache is 50. Dynamic RAM takes about 200 cycles. Storing data in an SSD, for example, takes about 100,000 cycles. And making a call on your local area network takes a lot more than 10 million cycles. Keep in mind that a cycle nowadays is about 0.5 nanoseconds. 1 nanosecond, just to keep in mind, is 1 billionth of a second. Let's just see what happens if we scale that up to 1 millisecond. Let's see how that changes. To access data from your registers, that would take 1 millisecond. L1 cache would take 4 milliseconds. L2 would take 10 milliseconds. L3 would be 50 milliseconds. Dynamic RAM storage would take 200 milliseconds. And to store in your SSD, you'd take 1 to 2 minutes. And for LAN network calls, we make an insane jump to more than 4 months. There's a lot more that we have not covered. This only scratches the surface. We've not talked about cache coherence. We've not talked about virtual memory. We've not talked about page tables. Now, is any of this information going to help you with your coding, with what you're programming? It depends. Probably not. In some cases, this is crucial. In other cases, it doesn't make much of a difference. But at least being cognizant of this lets you think about how to further optimize what you build.